Deep inside Japan's most advanced rail facility, a machine built for 400 kilometers per hour is taking shape.
"16 meters, 22 meters, two extreme aerodynamic solutions engineered to survive high-speed instability."
This machine was never meant to carry passengers. It was built to explore what happens at the edge of speed.
The manufacturing process begins with the extrusion of high-strength aluminum billets into precise structural profiles.
Uniformity in wall thickness is critical for the stability of the prototype at extreme test speeds.
With the base material formed, the individual profiles are prepared for integration into larger structural modules. The continuous seam strengthens the planar module for structural integration. Ultrasonic inspection verifies internal weld continuity across the full seam. Certified planar modules now advance towards structural integration. Planar structural modules are integrated into a continuous high-speed rail load-bearing framework. Reinforcement plates stabilize structural continuity before additional modules are introduced.
With the core structure assembled, surface refinement begins. The prototype now advances toward aerodynamic shaping in the next phase. The dual nose configurations are formed independently as hollow aerodynamic aluminum frameworks.
Sub-millimeter dimensional verification confirms structural precision before controlled release from the fabrication jig. The monocoque rib lattice defines the aerodynamic taper before surface sealing is completed. Each taper geometry is digitally verified against strict aerodynamic tolerances before structural release.
With structural fabrication of both experimental nose frameworks complete, each configuration proceeds to certified dimensional validation.
The independent high-speed Shinkansen bogie frame is fabricated from heavy-gauge steel to endure extreme dynamic loads at experimental velocities.
Vibration damping components are integrated to stabilize dynamic forces generated during ultra-high-speed experimental testing.
With the independent undercarriage assemblies finalized and verified, structural integration can proceed under controlled alignment conditions.
The internal infrastructure begins with the installation of a high-capacity electrical backbone and experimental fiber optic data network.
Thousands of sensors connect through this fiber network to capture real-time structural and aerodynamic data during high-speed trials. Each junction is verified to ensure stable and uninterrupted power distribution across all experimental systems.
With the internal electrical and data backbone secured, the instrumented structural shell is stabilized and prepared for comprehensive mechanical integration. At this stage, structural fastening is verified under strict torque control to ensure long-term integrity at extreme operating speeds. Alignment on Sector 4 is within tolerance.
Confirmed. Calibration check complete.
What's the reading on the starboard side? Measuring 0.5 millimeters out on the taper.
This spike right here indicates a potential subsurface anomaly.
Rerun the sequence and verify the coupling.
This section of the flat rail chassis looks good.
Agreed. Let's check the alignment on the forward structure.
With structural alignment confirmed, the prototype advances towards system integration and dynamic validation.
Instrumentation begins along the reinforced roof centerline, where aerodynamic measurement systems are integrated into the prototype structure.
Each sensor assembly is calibrated within controlled factory conditions prior to dynamic testing.
With roof instrumentation secured and calibrated, the prototype advances toward controlled systems validation and high-speed aerodynamic testing. Surface preparation begins on the 22-meter pressure reduction prototype. Controlled curing ensures uniform surface protection across the extended aerodynamic structure for high-speed validation testing. This section here shows a slight variance in the coating thickness.
Yes, I see it. Flagging it for manual review after the scan completes.
With functional surface treatment complete, the prototype advances toward controlled systems validation and integrated testing.
Factory validation begins. All systems are synchronized under controlled static conditions.
Each experimental sensor is calibrated for precision. Before dynamic testing, data accuracy must be verified down to the smallest measurement.
This spike here, are we exceeding the threshold?
It briefly touched the yellow zone, but it's pulling back now. Monitor the next cycle.
Calibration sequence initiated on the starboard side. Readings look stable.
Confirming data integrity. We are within the acceptable margin. With factory validation complete, the ALFA-X prototype is cleared for transition to controlled dynamic testing and high-speed track evaluation. From design to velocity, ALFA-X exists for one purpose: to redefine the future of high-speed rail.
NextGen Machine Works, building the impossible. Subscribe to join the future.